Hello and welcome to the AICE Chemistry Lecture Series. Today in this video we're actually going to do two sections of Chapter 7. We're going to go through Section 6 and Section 7 of Chapter 7 because they're very closely related to each other. Section 6 is naming compounds, so being able to go from the formula of a compound to its name based on oxidation numbers, so a bit of a different way of naming compounds. And then section 7 is going from the name to the formula. So doing the exact opposite process, but again with oxidation numbers. This section is going to explain why we see some of the names in AICE chemistry be a bit different than the names we learned in honors chemistry for things like potassium permanganate or nitrogen dioxide or the nitrate and nitrite ions and so on and so forth. So let's get started. Oxidation number in compounds and in ion names can be used along with some systematic naming that we learned last year to distinguish between very similar compounds of the same element. Usually this is especially going to be true of compounds that have oxygen in them or polyatomic ions that have oxygen in them. So for example, we learned that KMnO4 last year was potassium permanganate. That's what we named this. And that's because the permanganate ion, from what we learned, was MnO4 minus, that's what the permanganate is, and the potassium ion was K plus, right? So we put K plus and MnO4 minus together, we get KMnO4, so potassium permanganate. Well, with oxidation numbers, we can give this an alternative name. That alternative name is going to be based on the polyatomic ion permanganate. MnO4 can have the alternative name manganate 7. So we currently use prefixes to tell between the different elements in a group of oxyanions, right? So permanganate is MnO4 minus the manganate ion without the prefix, and I can't spell, manganate. Would be MnO3 minus. So we differentiate between the 3 oxygens and the 4 oxygens with that prefix per. Well, we can also show this difference through the oxidation numbers. So the manganate family, which is a manganese with oxygen combination, can also simply be named by the oxidation number of the manganese in the manganate. So potassium manganate 7 and potassium permanganate are just two alternative names for the same compound because permanganate and manganate 7 are two alternative names for the MnO4 minus ion. The manganate comes from the families, the manganese and oxygen ion family. And then the 7 in Roman numerals represents the oxidation number for the main non-oxygen element, in this case manganese in that ion. So manganate 7 is manganate 7 because in MnO4 minus, the oxidation number for manganese is plus 7. We can see some other examples of these in more common ions. Iron 2 and iron 3, for example. This we actually did last year in honors chemistry. We learned that when an element has multiple ions, we can use a Roman numeral with the charge of that ion in it in order to tell them apart. So FeCl2 and FeCl3 are two different compounds of iron and chlorine that vary because FeCl2 has an iron 2 plus ion, whereas FeCl3 has an iron 3 plus ion. And that's why we call this iron 2 chloride, or we call this iron 3 chloride. Well, another name for charges is oxidation states, because for an ion, its charge is the same as its oxidation number. So when we were using this last year, iron 2 chloride, iron 3 chloride, we were essentially using oxidation numbers to name and differentiate the two ions of iron. We just didn't know there were oxidation numbers at the time. We can also do this with covalent compounds that have oxygen in them. A lot of different nonmetals, when combined with oxygen, can form different versions of the same combination. And they differ by the ratio between the element and oxygen. For example, N2O, NO, and NO2 are three different ratio combinations of nitrogen and oxygen. And again, last year we used a different naming system, so we will call this dinitrogen monoxide. We will call this NO nitrogen monoxide. And we called NO2 nitrogen dioxide. So last year we used these prefixes, di, mono, and the di in dihydrogen monoxide to tell them apart based on how many of each element they had. But in another system, we can use the Roman numerals to do this. So essentially, all three of these compounds are nitrogen oxides. So together, all of these are nitrogen oxides. Because they're all combinations of nitrogen with oxygen. Well, we can differentiate the three nitrogen oxides by essentially just naming the oxidation number of the nitrogen. Nitrogen in N2O has an oxidation number of +1, so this will be nitrogen 1 oxide. The oxidation number in NO for nitrogen is +2, so this will be nitrogen 2 oxide. And in NO2, the oxidation number of nitrogen is +4, so this will be nitrogen 4 oxide. So this is another way of using oxidation numbers in order to differentiate compounds that are in the same family. And again, a lot of the times these will usually have oxygen associated with them. So now, why is this important? This is not important because you necessarily need to use this in your answers, but because you need to be able to identify these compounds when they're used in a question. So whether you, for example, the answer to a question was NO2, whether you say that's nitrogen 4 oxide or you say it's nitrogen dioxide, you will still get full marks because I understand that this is also a proper name for NO2. The difference comes in that if you're asked a question about nitrogen 4 oxide, you need to know what nitrogen 4 oxide looks like in the event that they don't give you the chemical formula. So if they use the term nitrogen 4 oxide reacts with hydrochloric acid, you need to know that nitrogen 4 oxide is NO2 to construct the equation. That's where this becomes important. And again, we can do this in all minus of situations. In another situation here, we can do the same for the ion family of the nitrate ions. So here we have what we would have called sodium nitrite and sodium nitrate. So NaNO2 will be sodium nitrite, whereas NaNO3 is what we called last year sodium nitrate. Now, these nitrite and nitrate come from the fact that nitrate is the NO3 minus ion, whereas nitrite is the NO2 minus ion. But the nitrite and nitrate ion can also be referred to as the nitrate family and using oxidation numbers to name them. So why would we call this sodium nitrate 3 when this is nitrite? Well, if this is part of the nitrate family, because it's a polyatomic ion with nitrogen and oxygen, the oxidation number here of the nitrogen is +3. So instead of calling this nitrite, we can call it nitrate 3, where 3 is the oxidation number of the nitrogen. And the sodium just comes from the cation being sodium. Similarly, here with the nitrate ion, because we have 3 oxygens, the oxidation number of the nitrogen is plus 5. So this nitrate ion, when we're referring to it as a family in the oxidation numbers, will be nitrate 5, because that's the oxidation number of the nitrogen. So when we put it together with a sodium cation, it will be sodium nitrate 5. And this is what those compounds look like. These polyatomic ions, if you do gotta remember, are polyatomic ions that are covalently bonded to each other, and they just simply have a charge. So the nitrogen and the oxygens are covalently bonded to each other, while the nitrate 5 ion is ionically bonded to the sodium ion. The nitrate 3 ion is ionically bonded with the sodium ion, but covalently bonded with it itself. So it's just another alternative way of naming these compounds and ions. So again, you don't need to use this when you're looking at your exam. You could stick to the nomenclature that you have learned last year, calling this potassium permanganate, calling this nitrogen dioxide, nitrogen monoxide, and dinitrogen monoxide, calling this sodium nitrite and sodium nitrate. Those are all still going to be perfectly valid answers. However, when you see sodium nitrate 5 on the exam, you shouldn't be confused. You should know that that's going to be sodium nitrate. When you see potassium manganate 7, which is very widely used on the exam, you shouldn't be confused. You should know that that's just potassium permanganate, and that 7 is referring to the oxidation number of the manganese. So let's look at some questions that are not necessarily going to use the nomenclature, but are going to use the fact that you can tell different families of compounds apart, or different compounds in the same family apart, by their oxidation number. In this paper 1 question, it reads, a student reacts 4 moles of ammonia with oxygen to produce an oxide of nitrogen and water only. Meaning that we are going to react, if we read this correctly, we react 4 moles of ammonia, so 4 moles of NH3, with oxygen, with O2, to produce an oxide of nitrogen. That means a compound made of N and O, but we don't know what these subscripts are. So we're just going to call them actually X and Y, not Y and X. So we're going to call these NXOY, meaning we don't know what the ratio here is, plus water. Each nitrogen atom increases its oxidation state by 5 in this reaction. So when we look at this, we can tell that the oxidation number from here to here of the nitrogen is going to go up by 5. Meaning if we aren't able to tell what the oxidation number here is for ammonia, we can then figure out what the oxidation number will be of this right here. So if we look at ammonia, hydrogen has to be plus 1 because the hydrogens are always plus 1 unless they're with a metal. That's plus 3 in total, so the nitrogen needs to be minus 3. If the oxidation number of this, or oxidation state, which is the same thing, of this nitrogen increases by 5, it goes from negative 3 plus 5, which will give us plus 2. So here, the oxidation number of the nitrogen, the product, will be plus 2. How many moles of oxygen gas react with 4 moles of ammonia in this reaction? So what we have to figure out now is, and I probably made this a little misleading, there's not a 4 here, but we have instead 4 moles of ammonia. So let's put that, I'm going to run out of space here, but 4 moles. So if we see here that we now know the oxidation number of the nitrogen in ammonia is plus 2, we can actually come up with what X and Y are. Because remember, these oxidation numbers are going to have to match. Meaning we know these nitrogen oxides, we know that this is going to be nitrogen 2 oxide. Because you know the oxidation number is 2. We know oxygen is -2. If this is +2, then we need 2 of these nitrogens to balance out 1 oxygen. So if the oxygen is -2, sorry, not 2, 1 of these nitrogens to balance out this oxygen. If the oxygen is -2, if nitrogen is also +2, then that means it's a 1-to-1 ratio between nitrogen and oxygen. So if this is a 1-to-1 ratio, we can now replace this X and Y with simple 1s, or essentially just make this NO. Because we know this is a compound. It produces an oxide of nitrogen, meaning a compound of nitrogen and oxygen. So they have to be neutral. So this is just going to be NO. From that, we can simply just balance this equation. So once we get to this point where we know what NO is based on that oxidation number increase, we can just balance out this equation and get our answer. If we have 1 nitrogen, that's balanced. We have 3 hydrogens, 2 hydrogens here. Now we can balance 3 and 2, so we're going to have to multiply this by 2, which I have 6 hydrogens, so we put a 3 here, so 6 hydrogens. 2 nitrogens, so we put a 2 here for 2 nitrogens. And that's why you have 2 times 1 is 2, plus 3 is 5 oxygens. So that's only 5/2. Or if we want whole numbers, we simply multiply everything by 2. So this is going to be 4. This is going to be 5. This is going to be 4. And this is going to be 6. And we can see that this is still balanced now with whole numbers, so 4 nitrogens, 4 nitrogens. 4 times 3 is 12 hydrogens. 6 times 2 is 12 hydrogens. And then 6 plus 4 is 10 oxygens here. 5 times 2 is 10 oxygens here. And so if we have 4 moles of ammonia, now we have a mole ratio, we can simply see that 4 moles of ammonia, which we had initially, is going to go into, so 4 moles of NH3 is 5 moles of O2. And they made this question really easy because the 4's just cancel out, and we can see that we need 5 moles of oxygen. Right, so you shouldn't actually need to do the math. Once you know this and you balance the equation, we see that it's a 4-to-5 ratio. Since we have 4 moles of ammonia, we need 5 moles of oxygen. So our answer should be B, 5 moles of oxygen. And if we look at our answer key here, that is indeed correct. So this, even though this is a balancing question and a mole ratio question, in reality, the essence of this question is redox and oxidation numbers. If we weren't able to figure out the ratio of NO here from the fact that the oxidation state of the nitrogen increases by 5, then we wouldn't be able to do the simple part of this problem, which is the balancing and mole ratio. All right. So that's why knowing these oxidation numbers and the fact that nitrogen 2 oxide would be NO is important to this test. Again, not for the answers you give, but for the actual logic behind some of these questions. That is it for sections both 6 and 7. This is a combination video where we're looking at both of those sections at once. I'll see you in the next video to go into section 8 of chapter 7.